In this section, we're going to talk about the ratio test and the root test. Let's start with the ratio test. So we're going to let the sum from n equals 1 to infinity of a sub n be a series with non-zero terms. And we're going to let rho be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So we're going to plug in n plus 1, and we're going to look at the ratio of a sub n plus 1 over a sub n. And this is typically going to be a complex fraction that we're going to have to simplify. We want to know what happens to rho, what happens to that limit of all of those positive terms, or the ratio of those terms. So if rho is between 0 and 1, including 0, but not including 1, then we say that this sum is going to converge absolutely if rho is greater than 1, or it goes to infinity, then that sum's going to diverge. And if rho equals 1, then this test is just inconclusive, and we've got to try something else to figure out what to do with that sequence and determine a different way to determine convergence or divergence. So let's look at a few examples. Part A, we're looking at the sum from n equals 1 to infinity of 2 to the n over n factorial. So let's review what n factorial is first. N factorial means I'm going to take n times n minus 1 times n minus 2, the way down to 2 and then 1. So for instance, 4 factorial would be the same thing as 4, well, there we go, 4 times 3 times 2 times 1. All right, so let's look at our ratio test here. We're going to take the limit as n goes to infinity. We're going to plug in n plus 1. So 2 to the n plus 1 over n plus 1 factorial. And we are going to divide it by 2 to the n over n factorial. When I divide fractions, I do keep change flip. So I'm going to keep that first one, 2 to the n plus 1 over n plus 1 factorial. I change the division to multiplication, and then I flip the second one. And we're going to have to simplify this. So here's what I know. 2 to the n plus 1. N plus 1 factorial is n plus 1 times n factorial. And now we're going to see some magic happen. So those n factorials are going to cancel, and those 2's are going to reduce. Remember, when we divide and we have the same base, we subtract the exponents. So I'm going to be left with a 2 in the numerator and n plus 1 in the denominator. And we know that that limit is going to go to 0. And since it goes to 0, then we would say that this converges absolutely. Let's look at the next one, part B. We're looking at the sum from n equals 1 to infinity of n to the n over n factorial. So we're going to take the limit as n goes to infinity, absolute value. We're going to plug in n plus 1. So n plus 1 to the n plus 1 over n plus 1 factorial. Divide by the original, n to the n over n factorial. Limit as n goes to infinity. When I divide fractions, I do keep change flip. Times n factorial over n to the n. And then I'm going to rewrite those factorials. So I'm going to have n plus 1 to the n plus 1 over n plus 1 times n factorial times n factorial over n to the n. We're going to see some things cancel. So notice that this n plus 1 to the n plus 1 over n plus 1 is going to reduce. So we're going to have just an n plus 1 to the n. When we divide and we have the same base, we would subtract the exponents. So n plus 1 minus 1 is just n. Those n factorials cancel. And then we're dividing by n to the n. So I could think about that as a limit as n goes to infinity, the absolute value. This is n plus 1 over n raised to the nth. And the limit as n goes to infinity, I could think about that as 1 plus 1 over n to the n. Now at this point, this should look really familiar. This is the definition of e. So that's going to e, which is not 0. It's about 2.7. So what that tells us is that this series diverges because that value for that limit is bigger than 1. And then let's look at C. And this is where you may want to pause the video and try it on your own. I'm going to rewrite the limit down here so I don't have to keep scrolling up. This is a sum from n equals 1 to infinity of negative 1 to the n over n factorial squared over 2n factorial. So I'm going to take the limit as n goes to infinity is a sub n plus 1. And then we're going to divide by the original. Then we're going to do keep change flip. So this would be n plus 1 factorial squared over, this would be 2n plus 2 factorial times 2n factorial over negative 1 to the n negative n factorial squared. So those negative ones are going to reduce. That's going to leave me with just a negative 1. And then when I take the absolute value, it's going to be positive. I've got n plus 1 factorial squared, which is n plus 1 factorial times n plus 1 factorial. And then I've also got a 2n factorial in the top when I multiply these fractions. And the bottom here, I'm going to have 2n plus 2 factorial, which is going to be 2n plus 2, 2n plus 1, and then 2n factorial. I've already reduced the negative ones, and I'm left with an n factorial here. Okay, so let's go through this again. I've got a negative 1 left over when I reduce the negative ones. I've got n plus 1 factorial times n plus 1 factorial. I've got 2n factorial, all that's in the top. 2n plus 2 factorial expands to 2n plus 2, 2n plus 1 times 2n factorial. And then I still have that n factorial squared, which is n factorial times n factorial. So I'm seeing some things cancel. Those are going to cancel. Once I take the absolute value, that negative is going to go away, and I'm going to expand that n plus 1 factorial. Is n plus 1 times n factorial, and that other one is the same thing. And I've got 2n plus 2, 2n plus 1 times n factorial times n factorial. So I'm going to be left with the limit as n goes to infinity of n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1. And I am going to multiply all that out because I know I'm going to have to use L'Hopital. So this is n squared plus 2n plus 1 in the top. This is going to be 4n squared plus 4n. Oh, this is 2n plus 4n, which is 6n, plus 2. So this is going to be infinity over infinity. We're going to use L'Hopitals. So I'm going to get 2n plus 2 over 8n plus 6. Again, it's infinity over infinity. So I'm going to use the L'Hopitals again. And I'm going to get 2 over 8, which reduces to 1 over 4. So that limit's going to be 1/4. And according to our rule here, since that limit is a value between 0 and 1, then this thing converges absolutely. And since it converges absolutely, it definitely converges. So that was those 3 examples. Now let's look at the root test. So we're going to consider the series from n equals 1 to infinity of a sub n, and we're going to let rho equal the limit as n goes to infinity, and we are taking the nth root of the absolute value of a sub n. If that limit is between 0 and 1, not including 1 but including 0, then it converges absolutely. If we get a value bigger than 1 or it just goes to infinity, then we say that that sum is going to diverge. And if we get 1, this test is inconclusive when we got to try something else. So let's look at a few examples. The root test really comes in handy when I have things raised to an nth power. So let's look at that first one. I got the sum from n equals 1 to infinity of n squared plus 3n, all that's raised to the n, over 4n squared plus 5, and that's raised to the nth power. So this is where I'm going to use that root test. So I'm going to take the limit as n goes to infinity, and I'm going to take the nth root of n squared plus 3n to the n over 4n squared plus 5 to the n. And my root rules say that I could take the root of each one separately, the top and the bottom of the fraction. So this is going to reduce to the limit. Well, I forgot my absolute value here, but this is going to end up being positive since I'm just adding a whole bunch of positive terms together. So this is going to end up being n squared plus 3n over 4n squared plus 5. And so as n gets larger and larger, this thing's going to head to 1/4. To show that, we could use L'Hopital's. So this would be 2n plus 3 over 8n. And then again, that's infinity over infinity. So we're going to take the limit as n goes to infinity of 2 over 8, which is 1/4. And since 1/4 is a number between a 0 and 1, we would say this thing converges absolutely. Let's do the same thing for b. Notice the top and bottom are both raised to the nth power. So we really could think about the sum from n equals 1 to infinity of n to the n over ln of n, and then that ln raised to the nth, as just n over ln of n, and then that whole thing raised to the nth. So take the limit as n goes to infinity. Now we're taking the nth root of n over ln of n raised to the nth. We're looking at absolute value here. This is always going to be positive. So that nth root and that nth power cancel out. I'm looking at the limit as n goes to infinity of n over ln of n. Again, this is L'Hopital's because I'm in the form of infinity over infinity. I'm going to take the limit as n goes to infinity. The derivative of the top is 1, derivative of the bottom is 1 over n. And if I take the limit as n goes to infinity and reduce 1 over n, that's really just n. And that's just going to infinity. And since that's heading to infinity, then we would say that this diverges.